Good morning, professors. We are from Ching Middle School. I am Chen Sihi from Form 2, and this is my partner from Form 4. And today our topic is rational distance in rational-sided triangles. In this project, we consider the formulas and the rationalities of the deviance, the distances between vertices and the centers, and also the perpendicular distances between sides and the centers. We start from considering ortho center and circumcenter, and then move on to in-center and Fermat point. And in this project, we let ABC be the lengths of the sides. And when we are discussing rational distances, we always suppose they are rational. And we let lambda equals to 4 times of the area ABC. And a triangle is called a Huronian triangle if its size and area are all rational. This following table shows some examples of Huronian triangles by a well-known generator. And as we can see, all its size and area are rational. And we will consider some rational distances, namely the free heights in Huronian triangles. And we ask for Huronian triangles, will the free heights be rational? And we get theorem 2.2, which is a formula between the free heights and the free sides. Therefore, given ABC rational, lambda is rational if and only if the free heights are rational. And this table verifies our result. And given a Huronian triangle, all its altitudes are rational. And we would then define the values of L and D as the distances from ortho center to other points as shown. And we ask for Huronian triangles, will the values of L and D be rational? And by using the property, we get theorem 2.5. And therefore, given ABC rational, lambda is rational if and only if the values of D and L are rational. And this table verifies our results. And as we can see, the values of H, D, and L are all rational. And as we can see, the right angle triangles is a special case in this table. And we will then move on to circumcenter. We first define R be the distance between the circumcenter and the free vertices, which is equal to the circumradius in this case. And we let PC be the perpendicular distances between the circumcenter and the sides. And by using similar techniques, given ABC rational, lambda is rational if and only if R and the values of P are rational. And this table verifies our results. And this is a summary for ortho center and circumcenter. Given ABC rational, the values of H, L, D, R, and P are all rational if and only if lambda is rational. And we will then move on to in-center, which is not as simple as the two centers before. We first let the values of T, S, and R as shown. And we ask for Huronian triangles, will the values of T and S be rational? By theorem 2.14 and 2.17, TATBTC and SASBSC can be expressed in terms of ABC with square roots. And by multiplying the values of T in theorem 2.14, we obtain this equation. Hence, given ABC rational, TATBTC are rational implies that lambda is rational. And it's naturally to ask if the converse is true or not. That is, given ABC rational, is lambda rational implies the values of T are rational? Unfortunately, this table shows some counterexamples. That means given a Huronian triangles, their angle bisectors lengths are not necessarily rational. And we want to further restrict the triangles into stronger conditions. And we ask for Huronian triangles, in what condition will the length of the angle bisector be rational? But to continue, we shall first consider R. And we ask for Huronian triangles where R belongs to Q. And by considering the area, we derive the formula for R. Therefore, given ABC rational, lambda is rational if and only if R is rational. And we'll now move on to conditions on angle bisectors and angles. We first define alpha, beta, gamma as the angle as shown. And we get these formulas. And we then define a right angle triangle with all rational sides is called a Pythagorean triangle. And if theta is an angle of Pythagorean triangle with theta not equals to 90 degrees, then tangent theta and sine theta will be rational. And by theorem 2.24, if alpha and beta are angles of Pythagorean triangles, then gamma is also an angle of a Pythagorean triangle. And by theorem 2.25, if alpha and beta are angles of Pythagorean triangles, then all the values of t and s will be rational. And this table verifies our results, in which we first determine tangent alpha and tangent beta, which alpha and beta are angles of Pythagorean triangles. And then we can generate a set of Huronian triangles, and all its angle bisectors will be rational. Previously, we obtained the values of the size t and s when given tangent alpha and tangent beta. But here, given a Huronian triangle, we want to consider a filter, which is a method to test whether the angle bisectors are all rational. We first define x, y, z be the lengths of these segments, and we get the equations for x, y, and z. And we will then define zt, which is equal to tangent theta, such that theta is an angle of a Pythagorean triangle. And given ABC lambda rational, we can obtain rational values tangent alpha, tangent beta, and tangent gamma, because lambda is rational if only if R is rational, if only if the values of tangents are rational. And note that tangent alpha, tangent beta belongs to T implies that sine alpha, sine beta belongs to Q. And hence, by simplifying, we derive the formulas for the values of tangents. And then we get a result as follows. Given ABC rational, if tangent alpha, tangent beta, and tangent gamma belongs to T, then the lengths of the angle bisectors will be rational. Here are two examples. In example 1, because tangent alpha and tangent beta belongs to T, and hence the values of T are rational. In example 2, because tangent alpha, beta, gamma are not belongs to T, and hence the values of T are not all rational. And in conclusion, tangent alpha, beta, and gamma determines the rationality of the values of T. Moreover, the values of T are rational if only if the values of T tangents belongs to T. And this is our two methods that we used. And finally, we will move on to Fermat point. We first let f be the Fermat point of triangle ABC. And the Fermat point of a triangle is defined as a point such that fa plus fb plus fc is minimized. And we ask for triangles with the values of f be rational. We first let sigma equals to the sum of the three lengths. Then we can derive the formulas. And note that sigma is rational implies that the values of f are rational. By considering the included angle, which is all equals to 120 degrees, and by using cosine law, we get the equation for sigma. And notice that we rejected the case of -4 square root 3 times the area of ABC by proposition 4.11. And hence 4 square root 3 times the area of ABC is rational implies that sigma squared is rational. And we'll consider two cases. And first, we'll consider two trivial cases. If angle C is 60 degrees, then we found out that it is not possible given in our reference. And if angle C equals to 120 degrees, then its general solution is given as shown. And we generated some triangles using the above formulas. And as we can see, the triangles are with angle C equals to 120 degrees, and sigma is rational. And we will now consider the general case. We use the following formulas, and notice that ABC obtained from the above will satisfy the triangle inequality. And by the above generator, and we substitute the obtained ABC into the following formula to see whether sigma is rational or not. And we constructed an indirect way to see if sigma is rational or not. And here are some examples of the value of sigma and the values of f. Thank you.
Thank you very much.